Hello, and today we are going to be talking about relativity. So, what is relativity? Relativity is the dependence of various physical phenomena on relative motion of the observer and the observed objects, especially regarding the nature and behavior of light, space, time, and gravity. Now, relativity comes in two flavors: general and special relativity. So, in one word, relativity is the most accurate theory that we know of till today to explain gravity. And what is general relativity? General relativity is the theory and a generalization of special relativity to consider non-inertial frames of gravitation, and is one of the most elegant and beautiful scientific theories known to mankind. One that almost enforces an Einsteinian belief in a universe that is characterized by simplicity, beauty, symmetry, and structure. As Einstein worked for the equations of his general theory of relativity, he realized that massive objects caused a distortion in spacetime. Now, imagine having a trampoline. And now you set a massive object in between it. It will warp downward as the elastic on the trampoline stretches downwards, pulling the mass, pulling the whole thing downwards, right, causing it to create a dimple effect, as we would like to call it. So we have, this is what it looks like, and we have a dimple effect going inward inside the warping or the dimpling effect. This is what it looks like. Now, what is general relativity in general? Now, general relativity, as known as the general theory of relativity, is a geometric theory of gravitation, which is just gravity. Now, also published by Einstein in 1915, the current description of gravitation in modern physics. General relativity has been described as the most beautiful existence of physical theories. It also generalizes relativity and special relativity and Newton's law of universal gravitation. Examples of such differences include gravitation, time dilation, gravitational lensing, the gravitation redshift of light, and the gravitation time delay. Now, what good is general relativity? General relativity provides immense insights on the deep, profound connection between mass and space-time. So we have a mass, let's say, launched into space, where we are more concerned about space and time. Now, in relation to these two things, we have something known as space-time, which is literally just a connection of space and time. Albert Einstein, in his special relativity, determined that the laws of physics are the same for all non-accelerating objects. So we have a observer here, okay, and the speed as they see it, let's say this observer sees another student or child throw a ball going in this motion. The observer, as he views this, is going to be the same. The laws applied to this observer are going to be the same as applied to one that is passing by in a car. Now, what is special relativity? Special relativity is just a theory. It was proposed by Albert Einstein in 1905. He also determined that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum was independent of the motion of all observers. This was the theory of special relativity. It introduced a new framework for all of physics and proposed new concepts of space and time, also known as space-time. Einstein then spent 10 years trying to include acceleration in his theories. And then he finally published his theory of general relativity in 1915. He also determined that massive objects cause a distortion in space-time, which is felt as gravity. So, in general, we have massive distortions. We have I don't know what to use. Let's say we have a circle, a sphere actually. We have a sphere thrown into space. Now, this sphere causes a disruption or a disturbance in space, creating a warp or gravitational wave, as physics likes to determine it. To create a wave around a disruption, which then affects space-time, which is the relation between space and time. And what is space-time to us? On Earth, as we feel it, it is known as gravity. Now, what is gravity? It is the pull of forces to the center of the Earth, which is the core, right? Which has the formula: force of gravity is equals to mass times gravitational acceleration. And what is the point of this, right? Like, why would you spend all your life, why would you spend 10 years trying to add acceleration into gravity, into space-time, into what is the point of all of this? Albert Einstein, in his theory, determined that the laws of physics are the same for all non-accelerating objects. So we have this object staying stationary. As a viewer on the Earth, we see this moving, let's say, at 1 light year. And we have also another object, let's say a satellite, and we have people sitting in there trying to view stuff, right? If this observer experiences this in 1 light year, the satellite, even when it's moving, let's say it's moving this way, right? Even when it's moving, it would experience the same thing as 1 light year. That was his special relativity theory. It was proven in 1916. In Albert Einstein's original pedagogical treatment, it is based on two postulates. The laws of physics are invariant, such as identical, in all inertial systems, such as non-accelerating frames of reference. Now, the second way is the speed of light in a vacuum is the same for all observers regardless of the motion of the light source, which is what we just explained. It doesn't matter what light it emits. It does not matter how fast it's moving, and it does not matter how fast you are moving. Be you stationary or be you in motion, you will still experience the same amount of gravitational laws affecting the sight of this object. So we mentioned in this drawing, we mentioned gravitational waves. So what are gravitational waves? Gravitational waves are ripples. As you see in water, you drop a pebble into water, you see the effect of circular motion around an object as you drop it in water. Those are ripples. Gravitational waves are almost the same thing. They are practically ripples, but in the fabric of space-time, caused by some of the most violent and energetic processes in the universe. Einstein also predicted that the existence of gravitational waves in around, I believe, 1916 in his general theory of relativity, and he proved it using his math skills and everything. His mathematics showed that massive accelerating objects, such as neutron stars and black holes, going, let's say, this way, and black holes, right? Okay, so we have neutron stars and we have black holes. Okay. It was originally proposed by Einstein in, I believe, 1905 with his special relativity. In 1916, he proved it with his maths, and it showed that these two things, neutron stars and black holes and other massive, huge objects in the gravity with acceleration, of course, right, would disrupt space-time in a way such that the waves of distorted space would radiate from the source, like the movement of waves from a stone thrown into the pond. Furthermore, these ripples would travel at the speed of light through the universe. Now, can you imagine ripples in a water or in a pond, let's say, traveling at the speed of light? That is a very, very fast speed. Traveling at the speed of light is almost impossible for the human to structure into water, but these gravitational waves move through it that way. Though gravitational waves were predicted to exist in the 1916, actual proof of their existence of gravitational waves was proven in 1974. Now this is 20 years after Einstein passed away. Can you believe it? 20 years after you're dead and you prove something? Anyways, in that year, two astronomers. So we have two astronomers. Oh wait, we have two of them. Sorry. Okay, so we have two astronomers going through space, right? And I believe they were working at Arecibo Radio Observatory, which is based in, I believe, Puerto Rico. They discovered a binary pulse. Two extremely dense stars and heavy stars in orbit around each other. So this one is, let's say, this is his field of motion, and this one has this field of motion. Alright, they're orbiting around each other like the Pisces, right? And this was exactly the type of system that, according to general relativity, should radiate gravitational waves. Knowing that this discovery could be used to test Einstein's audacious prediction, astronomers began measuring how the period of stars' orbits changed over time. After 8 years of observations, it was determined that stars were getting closer and closer to each other at precisely the rate that was determined in Einstein's general relativity. And these stars orbiting each other were repelling with gravitational waves. These effects were quite strong to be felt, and as we were saying, these were coming closer, and they were coming closer at the rate that Einstein predicted in 1916, which is about 58 years before it was actually noticeable. This system has now been monitored for over 40 years, and the observed changes in the orbit agree so well, extremely well with general relativity. There is no doubt that it is emitting gravitational waves. These gravitational waves impact human lives and everything, as we see on a daily basis, on a regular, as gravity. And this is Einstein's. Let's just have a little Einstein in there, This was Einstein's theory of general and special relativity. Thank you for watching. Have a good day, and come back for more.